of the series. Part 2 will be next week at the same time, so Tuesday, October 29th at 3 p.m. Eastern Time, and November 5th at 3 p.m. Eastern Time. The objective of today's series, or the three-part series, it's on performance-based design. So a few of the objectives that we'll be covering is number one, we're going to be actually understanding and going over the basics to performance-based design. And with that, we're going to be understanding the code and the criteria that are recommended for performance-based design and going into understanding the concepts of nonlinearity and the soil spring definitions. And finally, um, fourth is to actually go over the techniques to compute the rebars and the concrete strains for plastic hinge locations and to conduct pushover analysis on a portal pier and evaluate the performance. And last, it's to conduct a nonlinear time history analysis on the bridge itself. So without further ado, I'm going to introduce our speaker for this session. His name is Prathamesh Vain. He's one of our graduates with the Masters of Seismic Analysis, Seismic Focus. So he will begin the presentation, and I hope everyone is able to hear and see the screen. And I'm just going to do one final notification. If everyone can see or hear the screen, if you guys can do a quick hands up react button. Oh, excellent. Okay. Well, Prathamesh, it's all you. Thank you.
Thank you. Thank you so much, Beda. So, I welcome you all for this particular webinar series. So, as mentioned earlier, we will primarily focus on the performance-based design approach. And in the first part, we will be focusing on the response spectrum analysis entirely. So, the contents of the presentation would be like this. We will first cover the basics of the performance-based design. We will see certain failures in the bridge under different earthquake scenarios. We will go under the CSA 619 recommendations for PBD. Then we will be covering the secant soil stiffness calculation and how to update them in the program. And finally, we will be doing an analysis of an integral bridge by PBD approach, firstly based on the response spectrum analysis. So let's get started. Uh, so first things first, the basics of PBD. So before going to the performance-based design approach, we all know that historically we were following the force-based design approach, which is also called as the FBD. But with time, there was a modification in the methodology that we adopt for the seismic analysis of the structure. But before going to the performance-based design, it is very important to know why there was this shift in the analysis criterias from force-based to performance-based. So if you look at this particular graph on your screen right now, the red color curve would be indicating the demand which is under a particular seismic event. Now, the orange color curve is basically the capacity of your structure, or uh, now, when you're going to design this particular structure, what we do is we multiply this particular demand by a response reduction factor R. So the reduced response of this particular structure to the seismic event will be evaluated somewhere here. Right? So when we multiply or divide the demand with respect to R, the VDS, or the shear design force that we are getting in this particular structure, comes somewhere here. And then we multiply with the factors of safeties on the loads as well as the material, and we design or the structure at this particular level. So if we look at the demand and the capacity of the structure that we see, there is still a difference. But most of the times engineers are under this false impression that like we have used all the factors of safeties and our structure is going to be very safe under the earthquake, but it's not so, and it can be very well answered with the difference in the demand and the capacity of the structure. So this response reduction factor R is somewhat a theoretical concept that we have introduced. So how do we calculate this response reduction factor R? So the calculation of R is primarily based on the two principles, that is the equal displacement principle and equal energy principle. Now these two principles are actually been developed on the basis of the past earthquake scenarios that we had for the structures and what was the behavior of the structures under this earthquake scenarios. So based on that, some formulations were developed to calculate the response reduction factor R. Now, if you look at the first concept, uh, it is based on the equal displacement principle. So, if you are having a long period structure, so mostly a structure which is having a fundamental period of greater than 1 second, it is called as a long period structure. So for the long period structure, even when a structure experiences a non-linear behavior under seismic loading, its maximum displacement will remain relatively similar to the displacement it would experience under purely elastic conditions. So regardless of strength, the structure will remain entirely elastic in the seismic event. That's our assumption. And depending upon that, we say that the area of this particular curve, that is the total elastic and the hypothetically totally elastic structure, and the area covered by the actual or the inelastic structure, the energy which is dissipated in both the events remains same, and on the basis of that we compute that R is equal to delta U upon delta Y, which is nothing but the ductility, and finally we say that R is nothing but mu. Now this particular mu is basically nothing but the ductility, and depending upon the past experiences, we have calculated the response reduction factor R by evaluating the structural performance under different scenarios. Similarly, if you are having a short period structure, then in that case, we say that for a short period structure, the maximum elastic absorbed energy remains the same during the excitation. So it is not about the displacement now, it is about the maximum absorbed energy. And on that basis, this factor R, that is our response modification or the response reduction factor, is calculated as under root of 2 mu minus 1. So based on this, scientists or the researchers have already come up with certain R values for different types of structures. So for a single column pier bridge that we are having, we say that the response reduction factor or modification factor will be 4. While if there is a multiple column bend structure, the response modification factor would be 5. So the reason is quite simple. So in a single column structure, the failure of the structure will happen once the column fails. And when we are having multiple column bends, there is a high chance of energy dissipation depending upon the different column scenarios or the column configurations that we are having, and hence the energy dissipation is high, and so is the ductility, and that's the reason why we are having a higher response reduction factor in case of these structures. So from this we understand that most of the force based design principle revolves around this response modification factor, and most of this concept is based on the past experiences. Hence, like when we try to design a structure with the help of the FBD approach, we are not sure what will be the exact performance of the structure because we are not designing the structure or we are not evaluating the structure for its performance, or we are not evaluating the structure for the displacement that it will attain during a seismic event. And that is the reason why the problem that we are facing is we cannot assess what would be the structural um, state after a seismic event, whether it will be collapsed, whether it will be serviceable, or whether it will develop cracks. We do not know when we use the force-based design. And that's the reason we shifted to the performance-based design approach. So we say that the design methodology in which the structural design criteria is expressed to achieve a performance objective is called as a performance-based design. So the conventional design limits are applied on the forces or the member forces, but in case of the performance-based design, the limits are applied on the displacements or the strain values. Now, simply speaking about the principle of the performance-based design, so you see that there are two curves given here. So the capacity curve and the demand curve. So the demand curve is nothing but our response spectrum, and the capacity curve is nothing but the base shear versus the displacement graph or the pushover curve that we are having. So to evaluate the performance of the structure, what we do is we reduce the demand of the structure, as the demand will be basically with respect to a way such that what we do is we match the damping of the structure that it will face during a seismic event, so that the demand and the capacity of the structure are met at one particular point, and that particular point is called as the performance point. So at this particular point, the damping that will occur in the actual event is equated with the actual damping simulated in the structure. So that particular point we term it as a performance point. So we actually need to have a particular point so that the capacity curve and the demand curve are meeting together. So this is the theoretical concept that we are having with respect to the performance based design. But now let us compare first the PBD and the FBD together, and let us find out the limitations of FBD. So as we have discussed, the FBD completely ignores the interdependency of the strength and the stiffness. So the variation of the response reduction factor from code to code is there, and the there will be a different structural performance under different codal recommendations. So which is not true under one particular seismic event. So that is ignored. The system ductility is not considered at all. Then we do not know what is the post-earthquake performance of the structure, and as there is no reliable quantification of the R value, and thus we could not predict what would be the structural status. Then the limitation of FBD to the various seismic load resisting systems. So we know that there is always a research going on and a new load resisting systems in terms of, let's say, different types of damper systems or base isolation systems, etc., come into the picture every day. And these systems are not tested in the past earthquakes, and thus the prediction of the performance of these systems is not possible by using the force-based design approach. And hence, uh, due to this limitations, the performance-based design comes into picture. So under the performance-based design, the quantification of the performance of the bridge is possible. All the structural systems which are not covered in the code can be easily covered by performance-based design. There is a shift from the strength criteria to the performance criteria. So for bridges who hold the response control devices, the quantification of performance of those bridges is possible. And Reliable estimate of the structural response in aftershock is also possible by using performance-based design. So if this is clear, let us now move on to the failure of the bridges under earthquake. So it is very important for an engineer to understand what would be the failure of the bridge looks like so that we could develop uh, a certain restrictive or some conservative measures to restrict the failure of that particular bridge under the seismic event. So the probable failure mechanisms should be known prior to modeling or designing any structure. So these are some of the probable failure mechanisms that we have seen in the past earthquake, and we can ensure that, or we can predict that such type of failure mechanisms would be possible in the upcoming scenarios as well. So on the left, if you see the ductile failure of the column in flexure, so this is a very common type of failure that we observe. So at the bottom, we can see that the concrete has fault, and it means that it is a region where the plastic hinge is formed. That is, our structure at that particular part, the concrete is gone into the plastic region, and the plastic hinge has developed. So that is the flexural failure. Similarly, on the right, if you see, it's a brittle failure of the column under shear. So due to the failure of the shear reinforcement, the concrete, as it is brittle in shear, a sudden failure of the section, column section, is observed. So these are the major type of failures that we see, but also sometimes we as engineers would ignore the failure mechanisms which are unsitting of the deck or pounding between the deck. So this seems to be very unlikely event, but it's been observed in the past earthquakes as well, wherein the deck has completely cut off the bearings and fall down. And similarly, if there is an EG been provided between the two spans, there is a possibility that these two spans pound at one particular location and cause damage, and hence the serviceability of the structure is compromised. Similarly, the foundation soil failure where there is settlement of the foundation or the development of cracks in the foundation is also need to be checked, and also the abutment backfill soil failure, wherein we could see that there is a severe fill settlement that was observed in one of the structure after the seismic event. So these failure criteria needs to be considered by the engineer before uh, completing saying that the design of this particular structure is complete. So let us now go to the process flowchart that we generally have when it comes to the design of any particular structure. So this process flowchart is basically divided into two parts. So the first part covers the initial design by EDA, or the response spectrum analysis, we could say, and the second part considers the performance demonstration and capacity design. So coming to the first part, uh, so firstly we do the estimation of the dimensions of the structural members, then we estimate the stiffness, incorporate the members and initial stiffness by soil springs based on the PY and the TZ data which is provided to us by the geotechnical engineers. Now we determine the period of the structure under the soil structure interaction and run the response spectrum analysis. Now here there is this important step that we need to do, and which is a very cumbersome approach that we follow, is to check whether the spring displacements are consistent with the assumed stiffness, because under the response spectrum and the eigenvalue analysis, the soil spring stiffness, which are actually non-linear in nature, we consider them to be linear and evaluate the structure. So we need to check whether the spring displacements are within the limit or not. If they are not in the limit, Then we need to recalculate the spring stiffness and update the model and rerun the analysis. So this loop continues until and unless all the spring stiffness are uh, or the criteria is met, and the analysis further continues to evaluate the structure under the earthquake, and we find the global bent displacement. So on this basis, the design of the structure is generally um, been taken care of. Once we are good to go with the design, then we need to evaluate the performance of the structure. So once we have decided on the initial sizing and the preliminary design based on the response spectrum analysis, we carry out the pusher analysis or the nonlinear time history analysis with the compatible time histories to compute the capacity of the structure, and under that we evaluate the maximum strain requirements. So if the strain requirements which are prescribed by CSS 619 are met for that particular structure, we say that the structure um, is having a particular performance level, and if those criteria are not met, we revise the design and go back and check whether the strain requirements are met again or not. So once this process is complete, we check whether the capacity design checks are satisfied, and if these checks are satisfied, the complete design or the complete performance based design concept uh, is satisfied. So this is the ideal flowchart that we follow. Now let us go towards the CSS 619 recommendations for the performance based design. So firstly, we need to specify what is the hazard level. So there are three types of hazard levels specified in CSA. So the 2% in 50 years, having a very high return period of around 2500 years, is generally useful for the force-based design and also used in the performance-based design. Other hazard level that we consider is of 5% in 50 years and 10% in 50 years with the corresponding return period. So if you see that the hazard levels that we are seeing here are very uh, are having a very large return period as compared to the hazard levels that we see for the floods and the winds, wherein we consider a return period of, let's say, 30 years, 50 years, right? So this says that the seismic event is a very rare event and will be having a very high demand forces on the structure, and hence it is very important to design the structures accordingly. So depending upon the importance categories that the bridge can be categorized in, there are three categories that are defined. So firstly, uh, there is a lifeline bridge, which is basically the structure of utmost important in the region. And if there is a serious damage to this particular structure, there is a great harm to the regional security. Economic recovery of multiple region is been compromised. So these are the lifeline structure. Then we have the major root bridges. So the major root bridges, we require that these are active under the post-earthquake scenarios for the emergency responses, and the impact of this particular bridge damage will be on the entire region, the commerce and economic recovery been compromised for. So these structures are called as a major root bridges, and the remaining all the bridges are called as a minor or the local root bridges, wherein redundant access is possible and it does not impact a very large area. So the classification of the importance category is basically based on the owner of the structure. Then basically the seismic performance category, there are three seismic performance categories that we are having. So let's say, for example, if the fundamental time period of the structure is less than 0.5 seconds. So let us say that for a structure which is having a fundamental period of, let's say, 0.3 seconds and having SA zero point 0.2 in between zero point 0.2 and 0.35 G, and if we are having a lifeline structure, then in that case the seismic performance category will be 3. So on this basis the seismic performance category is classified. So based on the seismic performance category that we are having, so let's say we are having a performance category of 3 and we are having a major root bridge, then in that case the code recommends us, or the code insists us to evaluate the structure under the performance based design approach. So the regular or the irregular structure classification is also been done here. It actually depends upon the maximum skew angle or the subtended angle at the region. So based on the service, we have 4 types of performance levels. So immediate, limited, service disbursement, and the life safety. And similarly, based on the damage, minimal, repairable, extensive, or probable replacement are the uh, performance criteria which are mentioned in CSA. So depending upon the damage level and the serviceability limit that we are having, so let us say that we are considering the service disruption and the extensive damage level, then in that case, the concrete strain in the structure should be limited to zero point 0.8 epsilon Cu, and the steel strain in that case shall be limited to 0.05. So these strain limits are given in CSA, and depending upon the service and the damage level, we can choose or we can evaluate our structure to check whether these strain limits are met or not. So these strain limits are similar to the one given in AASHTO as well, but in AASHTO we could see that additional information such as the axial force or the axial force coming on to the element, or the what is the configuration of the reinforcement in the structure, etc., is required to evaluate the strain limits for one particular performance level. So for life safety, let us say the concrete compressive strain is calculated by this formula, and it is not at all a single numerical value as given in CSA, but it depends upon the axial force which is coming in the structure and the shear reinforcement configuration. Similarly, we also need to check for the additional measures such as whether the connections, the bearings, the restrainers, etc., are within the limits of their deformations. Also, we need to check about the foundation moment, and we also need to check whether the approach settlement is restricted or not. So with this small background, let us now focus on the analysis of an integral bridge with a PBD approach. So as I said, response spectrum analysis will be covered in this particular section, and we will be doing a certain iterations to see that the soil spring deformation is within the limits. So coming to the bridge model, so herein we could see that this bridge is basically a 3-span PSC composite type of a structure, and there are abutments at both the ends. Pile groups are present. It's a bent uh, with a portal type of a structure for the piers, and the piers are basically resting on the monopile. So for this particular structure, the location that we have considered here is BC. The soil type is considered to be soft. Importance category is it's a lifeline bridge, and depending upon this, the seismic performance category was SP3. Thus, the response modification factor in this case would be 5. because it is a multiple bent pier, and the performance level that we are considering here is the service limited. So the scope of the study will be to check the flexural damage level at the potential plastic hinge location. We will also assess the unsetting of the deck and the abutment longitudinal direction, and we'll also check the pounding between the deck and the abutment. So this will be the scope of the study. So as I said, 3-span PSC composite. Each span is approximately of 20 meters. The height of the pier is 7.4 meters. The monopiles are driven or casted at around 39.6 meter below the level, below the ground level. The structure or the superstructure is constructed of C45 pier, pile, and the pile shaft, or the substructure is constructed with C40 and C35 grade of concrete. So it is a 6 girder PSC composite type of a superstructure, and all the substructure is having a circular type of sections with the diameter mentioned here. Now, with this background, let us go to MIDAS Civil Annex to assess the performance of the structure. So, as I said, so this is the structure that I have modeled. Now, we are going to carry out the response spectrum analysis on this particular structure. So, let us go briefly into the model. So, if you are quite new to MIDAS Civil Annex, so briefly, Civil Annex is basically a latest version of MIDAS Civil, and it has the API related functionalities. So, we can utilize the API functionality to uh, carry out the parametric analysis by using Python, VBA, or as well as the inbuilt plugins which are provided in the structure. We can also utilize Grasshopper to communicate with MIDAS Civil to analyze and I mean the pre-processing and the post-processing of the structure. So in this particular structure, as we could see, firstly, let us see the boundary conditions that we have given for this particular structure. So we have given supports at each end. So let me just display the supports. So the supports are given at the abutment level at each end and at the bottom of the piles. Similarly, there are pile springs been given at the pile groups and the monopile shafts. So these pile springs are basically multilinear springs. So if I had to show the properties of one of the pile spring, so you could see that force deformation function is been given for each pile spring, and this data is basically been taken from the geotechnical investigation. So for the viewers, this is basically one of the actually constructed bridge or the on-site project that we are having here, and for this the pile spring data that we have got is basically converted into the force deformation function, and the force deformation function for each pile spring looks something like this. So we have applied this pile springs by using the multilinear objectives. Similarly, we have also given the result links. The static loads that we have considered in this particular structure is the sulfate, the SIDL in the form of the crash barrier as well as the wearing code. Now, for this particular analysis, we have not considered the moving load as a static load. But if we want to consider that as well, we can convert the moving load into a static load and give it as a static load here, and convert that into the loads to masses. So the masses for the eigenvalue analysis are considered as self-weight, which is considered internally by the program. Similarly, the wearing force and the crash barrier is converted into masses. So this is the configuration that we are having. Now, the response spectrum function that we have considered here is this. So this is basically depending upon the location and the site characteristic of the structure. We have considered the response spectrum function from the seismic demand calculator for CSA, and we have defined the response spectrum load case. So the response spectrum load case is basically been given in the longitudinal direction. The eigenvalue analysis data looks something like this. We have considered the number of frequencies to be 50. So for this particular structure, we carry out the uh, eigenvalue analysis first. So let us check the eigenvalue analysis results. So if you go to results and mode shapes, vibration mode shapes, I'll just apply. So the first mode that we are getting is basically in the longitudinal direction, and the second mode that we are having is in the transverse direction. Correctly so, the stiffness in the longitudinal direction will be lesser as compared to the transverse direction, because in the transverse direction the framing action will come into picture. So if you want to look at the time period of the structure, so the fundamental mode, which is our first mode, is having a mass participation of around 51% in the longitudinal x direction, and the time period for that particular structure is considered as 1.58 seconds. Now, the problem in this structure is that if you go to the properties of the point springs, we will see that the point springs are basically defined with respect to the multilinear function. So the initial stiffness that we considered in the definition of the point springs or the multilinear springs will be considered as, so the initial stiffness of the first 2 points will be considered for calculating the stiffness of the point spring, and on the basis of that, the eigenvalue analysis and the response spectrum analysis of the structure will be considered. But now we do not want that, as the structure is displacing, the soil is going into the nonlinear zone, and what we are interested in is to check the secant stiffness and not the initial stiffness of the structure. So for this, one method is to develop a Excel sheet wherein we can compute the deformation coming into the structure under the first iteration, and reassign the spring stiffnesses for that particular point. The so so the method that we generally follow is this. So we develop an Excel sheet, we compute the displacement, and on the basis of the displacements which are computed, we update the soil spring stiffness at each point, and on the basis of that, the soil spring data is modified, and we could observe that at each iteration the stiffness of the soil spring is reduced, and until and unless we find a value wherein the satisfaction of the displacement criteria is observed. Now, for the practicing engineers, it's a very tedious and a very cumbersome job to be done, because every time we need to change the soil spring data and update the model. So to make things simpler, what we have done here is we have developed a, a, a function which is called as an iterative response spectrum function, which is based on the Python script. And all the iteration jobs that we see here. So for this particular structure, for one particular pile, I did around 12 iterations to converge to this particular point. So what the iterative response spectrum dialog box will be doing for us is it will basically do this process automatically and give us the results. So let us say, how do we do this in the program now? So for this particular structure, I'll just open or unlock the structure entirely. Now we'll go to apps, and in the apps we have the API settings. For the API settings, I will connect my model with a Python script with the help of a mappy key. So once I do that, the Python script will be looking something like this. So this is the Python script that we have developed. So let me just run this particular Python script and we'll verify what are the changes which are taking place. So if you observe that there is no boundary change assignment been given here, and the structure groups are something like this. When I run this particular script, we'll see that the new springs at each node where the multiple or the multilinear springs were created is updated, and the analysis is running automatically. So this is the first iteration. The program will check whether the displacement is satisfied or not. If the displacement is satisfied, then that particular spring is not updated, and if it is not, the spring is updated. So at each iteration, the program will be uh, identifying the displacement locations or the deformation criteria, and the spring data will be updated automatically. So this would save a tremendous amount of efforts and time for an engineer. So the iterations will be carried on. So until and unless the convergence criteria is satisfied. So what we have done here, the convergence criteria that we have kept here is 0.05%. So which is a very stringent convergence criteria. So until and unless this deformation criteria or the tolerance is satisfied, the iterations will be running. But if we had to do this manually, we see that a very high convergence or the criteria has been kept, such as 5% to 10%. So just to save time. But with the program, the convergence criteria can be more stringent and more realistic to the actual conditions. So if you see the finally the convergence has been achieved. The maximum percentage difference that we see in this case is around 0.048, and convergence is achieved at the end of 8 iterations. So this is the iterative response spectrum approach that we have used. Now, to simplify the way in which this program has basically updated the soil spring is as here. So the program created the RS boundary group first. So this is my RS boundary group. If you see that it contains all the point springs. So the locations at which the point springs are given, the locations of those nodes is been identified and is been adapted in the RS boundary group. Similarly, other boundary group is created which is called as the RS boundary group for boundaries. So in this, the linear springs or the effective or the secant stiffness springs will be stored. Now, the program utilizes the boundary change assignment criteria. So if you go to properties, so you could see that for the time history, response spectrum, and the eigenvalue analysis, an RS boundary group is been assigned. So this RS boundary group is nothing but the linear point springs which are created by the program internally. So if we had to see what are the point springs which are created, so if I go to exactly to the group, so RS boundary group, so this is the point springs which is created. So this is created for the node 7838, and you could see the effective or the secant stiffness in X, Y, and Z direction. So earlier the Z direction was the same, and it will remain the same after change, but the multilinear springs which were assigned to Y and X direction, they are changed into linear springs, and this is done iteratively. So once we achieve this particular convergence, we can now check what is the actual period of the structure that we are getting. So I'll go to results and mode shapes, vibration mode shapes. So as anticipated, the period of the structure has increased because the stiffness of the soil springs has been reduced. So that is the reason the period of the structure has increased from 1.58 seconds to 2.08 seconds. Now, the other important thing that we need to always take care in this case is the effective section stiffness scale factors. So the section stiffness scale factors are basically calculated by uh, by considering the effective section stiffness, that is I effective. So for that we can utilize the GSD functionality. So the GSD functionality is one of the feature in MIDAS wherein we can calculate the section stiffness scale factor. So if we import the section into GSD, we can ultimately get the correct stiffness. So depending upon the axial force, so let us say that the axial force is around 6000 kilonewton, and on the basis of that we can get the correct moment of inertia for this particular section, and depending upon the section we can update the section stiffness scale factors and reassess the model uh, again. So for this particular structure, as the analysis is complete, I have already assigned the section stiffness scale factors. Now let us evaluate the results in this case. So firstly, we are interested in the structural drift that we are getting in the columns, and what is the deformations in the abutment level and the level of the EG or the EJs that are provided. So I'll go to the results, deformations, and the deformed shape. So for now, I have already given certain load combinations. So we could see that RSX plus zero point 0.3 RSY, 1.25 dead load plus earthquake load, and pointed dead load plus earthquake load. So these two are basically the ULS 5 load combinations. So under these load combinations, basically we need to assess the performance of the structure. So as we are assessing the demand coming or the coming onto the structure under the earthquake event, we'll go for the ULS 5 load combination. So I'll turn on the values, turn on the legends, click on apply. So for this particular structure, I want the structure to develop the plastic hinges at these locations, that is in the column and not in the piles or the pile group. So the drift that I'm checking here currently is the drift in the column. So the drift would be 0.373 minus zero point 0.3 in this case. And similarly, we could check the deformations at the abutment and the EJ level. So the results for this particular structure are now tabulated. So in RSX, that is the longitudinal direction, we get around 0.074 meter of deformation. And similarly, under the ULS file load combinations, we get this. And finally, the demand drift that we get under the response spectrum analysis is around 0.074 meter. This demand drift will be compared with the capacity drift under the similar performance criteria that we earlier discussed. And depending upon the comparison, if the demand drift is less than the capacity drift, then we can say that the performance uh, of that particular structure is achieved. And if it is greater, then we need to alter the design of the structure to satisfy the criteria. So currently we are limiting our discussion to the demand, and the capacity drift will be taken care by the pushover analysis in the next session. So the unseating uh, of the abutment in the longitudinal direction, the maximum displacement in the bearing, we got it as 0.17 meters, and for the pounding between the deck and the abutments, a very high displacement of 0.376 meter is been seen here. It means that we need to provide the seismic restrainers in this case for this particular structure. So this was the response spectrum analysis criteria that we see to evaluate the demand onto the structure. In the upcoming webinar, we will understand the nonlinear behavior in the structural elements. We will define the moment curvature characteristics to evaluate the plastic hinge representations. We will assign the properties to the structural elements for simulating the inelastic behavior, and we'll compute the strain limits under the different performance categories to evaluate the performance of this particular bridge. So this will be in the next session. So Beda, I'll hand over the stage to you.
Thank you. Uh, Thank you, Prathamesh, for that. I'm going to share my screen with some of the questions that came in.
Okay. So with the first thing, yes, the presentation slides will be shared with each attendee after each webinar. Then what adjustments are necessary for response spectra to account for the site-specific conditions such as soft soils or rock sites uh, near bridge location. So when we evaluate the response spectra, or we try to specify what is the demand um, response spectrum that we need to consider. So in that case, the soil categorization is basically done on the basis of whether it's a soft soil, rock soil, or etc. So this entirely depends upon the geotechnical engineer in that way to uh, let us know what is the average characteristic or the average Vs or the shear wave velocity that we are getting in that particular structure. So depending upon the average shear wave velocity that we are getting, the soil characterization is been done to evaluate the response spectrum demand in that case. So third question, can the higher modal effects be captured in MIDAS? So the answer is yes. So depending upon the number of frequencies that we suggest to the program, the higher modes are also considered in the program. So currently, as you've seen that the frequencies or the number of frequencies have been limited to 50 in this case, and thus the number of modes that we have considered is only 50, and the results on that basis were seen. Similarly, if we want to see the second order effects, then in that case also we can go about doing the buckling analysis, wherein the second order effects will be considered, and the buckling mode shapes will be also been calculated by the program. So coming to the fourth question, what are the limitations of RSA with nonlinear behavior? So uh, to answer this question, RSA is basically itself is a linear analysis. It is not a nonlinear analysis. So the limitations will be, as we saw earlier, the actual performance of the structure or the actual displacements of the structure will not be predicted by the RSA. It will be only an estimate of the displacement, because we are only catering for the response reduction factor or the seismic criteria with the help of the response reduction factor and nothing else. And thus, um the response spectrum analysis does not cater for any nonlinear behavior. Similarly, we do not see any criteria with respect to the ductility of the structure. So the strength and the ductility are the two most important things that we need to consider during the nonlinear analysis. In response spectrum analysis, we try to consider strength somehow, but we nowhere touch the ductility, or we touch the ductility indirectly with the help of the R factor, and which is a very indirect approach. So coming to the fifth question, how does MIDAS handle nonlinear behavior? So, so in MIDAS, the nonlinear analysis or the nonlinear behavior uh, can be handled in both ways, such as the material nonlinearity can also be considered, the section nonlinearity can also be considered. So we are having the nonlinear analysis tab, wherein you can specify both the material and the section nonlinearity. In terms of the plastic hinges or the hysteretic loops, depending upon the type of analysis that you are doing. So if you're doing a pushover, plastic hinges can be assigned. And if you're doing a nonlinear time history analysis, different hysteretic models are available in the program by which the nonlinear behavior can be captured. Coming to the sixth question, can civil simulate the progress of damage and predict failure mechanisms during seismic event? So uh, the progress of damage, if you mean that in terms of the crack propagation, so the answer for that is no. The progressive damage or the crack propagation could not be predicted. But if you mean the progression of damage is in the form of the failure mechanisms, or the pattern in which the plastic hinges are developed in a structure under a seismic event, then yes, MIDAS Civil can assess the mechanism of the plastic hinge development in the structure and could predict the damage depending upon the type of the hysteretic model that you have given. So, and also if you are given the fiber hinge type of a model, then the damage prediction in that case becomes more easy.
I think that concludes the questions for actually today. Actually, there a few more came in. Uh, Give me a second. Sorry, I apologize.
Even if we are designing the columns or the it is the initial design or the first step. The reason being, if you're not considering the response reduction factor, then in that case it means that you are considering the seismic demand 5 times more than the requirement of the code. Like assuming that the response reduction factor that you considered is 5, and the section sizes in that case that you will be getting will be very larger, and hence we can skip those, and we need to consider the response reduction factor in that case.
Okay. Another question is, in one slide you showed that for the 2% seismic level, we use force-based design, and for 2%, 5%, and 10%, we use PBD, performance-based design. Is this from the code?
Yes, that's correct. So if you go to the CSS 619, uh, the performance criterias are to be evaluated for the different hazard levels. So the depending upon the hazard levels that you're having. So let us say the return period is very small. So let's say 475 years or 10% in 50 years. So for this type of structure, what we anticipate is the structure should remain serviceable and there should not be any damage. So for that case, uh, in case of the performance-based design, the code asks us to evaluate the performance for the different hazard levels. So depending upon the owner's criteria that they have fixed, we can evaluate the performance under different hazard levels.
Okay. There's a few more questions. I'm just gonna try to list them out right here. I think that appeared on the screen, right,
Yeah.
Prathamesh?
Yes. So coming to the 11th question, uh, would the nonlinear soil springs behind the abutments reduce the deck displacement if considered in MIDAS model presented? Yes, you're right. If we are considering the nonlinear soil springs behind the abutment, uh, the deck displacements will be limited because it will provide the resistance to the structure. So currently, the nonlinear soil springs are not considered in this particular model. But if you want to consider it, the Caltrans SDC criteria provides the nonlinear spring stiffness to be used for the abutments in this case, and that uh, entirely depends upon the depth of the abutment and the angles. So the angle of internal frictions. So we can use that to compute the nonlinear soil spring stiffness uh, given in the Caltrans SDC.
Okay. And I believe there's one more question.
So the 13th question, how can we consider passive forces of the soil behind the abutments in RSA in MIDAS? So in case of the passive forces, so as one of our friend just mentioned in the previous question about the nonlinear properties for the abutment soil stiffness. So these forces can be considered in terms of the soil stiffness. So we can model the entire soil with the help of point springs and then utilize these springs to consider the passive forces coming on to the abutment.
Okay. Thank you, Prathamesh. I think that we'll stop it there for the questions. Um, just want to indicate that he will be presenting for the second part as well, which leads us to a few things. First, at the end of this webinar today, there'll be a very short survey. And what I mean by short, it just indicates whether or not you will be participating in part 2 and or part 3. That option is available. Second is there is going to be an option for downloading some of the tutorials for those who are users of the response spectrum and performance-based design related criterias attached to the presentation. I think you should see that already listed in the tool section of your um, control panel. So you could download the files there. If not, please let us know and I will forward this information over to you separately. And last, for those who are looking for the continuing education credits, what we'll do is at the end of the session 3, part 3, we will send out a mass certificate for everyone who's attended. So whether you attended one or all 3, we will send these to you via email as a certificate link. once the third session is complete. So on the 5th of November, you should receive an email with the links for your session with the credits. Okay, I believe that's it. Just want to remind everyone once again that part 2 for pushover analysis will be on October 29th at 3 p.m. Thank you, everyone. Thank you, Prathamesh, for your session today. We hope you have a
Thank
great
you.
day.